Hi everyone. Our goal for this video is to look at operations with imaginary numbers. The first operation we're going to be looking at is how you raise an imaginary number, or I, to a power. So by the end of the segment, you should be able to complete I to the 81st on your own with no problem. Before we can get there though, let's just start with I. So I is really I to the first, and as we defined in class, I is the square root of -1. Okay, since you can't actually take the square root of a negative number, mathematicians define this as imaginary. We call it I. So now if we want to square I, that really means expanded. We're multiplying I times I. And remember, we defined I as the square root of -1, so we can substitute that definition in for each I here. So really, I squared is just the square root of -1 times the square root of -1. Which we know from our unit on radicals that this is really like -1, the square root of that, squared, multiplied 2 times. And a square and a square root undo each other, so the square root of -1 times the square root of -1 is just -1. So I squared is really just saying -1. I to the third is really I times I times I. So similarly to I squared, we can go ahead and substitute in the square root of -1 for each I we see. So I cubed is really the square root of -1 times the square root of -1 times the square root of -1, which we see an I squared within this problem. So really the square root of -1 times the square root of -1 is just I squared, which we already defined to be -1. So really this is -1 times the square root of -1. Now you can't simplify this square root of -1 any further. So I'm just going to rewrite that in terms of my imaginary numbers again. This is really -1 I. Okay, and you don't really need the coefficient. If you're talking 1, we can just write this as -I. Okay, so I squared is equal to -1. I cubed is equal to -I. Okay, by substituting in the square root of -1 and solving. Okay, so let's look at I to the fourth. Actually, before we look at I to the fourth, let's look back at I to the third. Really, I cubed, you can expand as I times I times I, or you could really write this as I times I squared. Okay, and we know that I is just I, and I squared is -1, so we could have jumped from this step to this step here. So let's try this method with I to the fourth. I could expand this out as 4 I's, okay, or I can break it down into pieces that I already know. So I already know what I squared is. I could make this I squared times I squared. Okay, because remember, when you multiply, you add those exponents. And we know from above that I squared is equal to -1. So really, this is -1 times -1. Okay, -1 times -1 is just 1. Okay, so I is defined as square root of -1. I squared is -1. I cubed is -I, and I to the fourth is positive 1. Excuse me. Let's try the same process for I to the fifth. So the fifth can be broken down into I to the third and I squared. Okay, I could also break this down into I 5 times. I can do a lot of different things. This I to the third can be broken down into I squared times I, and then we still have one more I squared. So really, I squared is -1. I is just I. And we have another I squared is -1. Okay, I could have rearranged order to make it a little bit more clear, but hopefully you're still following along. If we simplify this up, we get -1 times -1 is just 1. And I times, well, we just have one I. So really, I to the fifth is just I. So notice we're kind of seeing a pattern here. So I started with I, I'm back at I again. Let's see what happens with the I to the sixth. So I can break I to the sixth down a few different ways. I think the best way to break it down is in terms of numbers. So, for example, I squared results in a number, I to the fourth results in a number. So I'm going to try and rewrite it in terms of I squareds and I to the fourth. So I can write this as I squared times I squared times I squared. Okay, and we all know that I squared is just -1. So really, I'm multiplying -1 3 times. So what's -1 times -1 times -1 is just -1. Okay, so I started at I, went to -1, and I'm repeating that process here. I started at I and going to -1. And that's because I actually can be solved in groups of 4. So up to I the fourth, we go square root of negative 1, I, 1. And this process is going to repeat. I have I, which is, I could technically write this one as the square root of negative 1. Then I go to 1. Then I go to negative I. And my last one of the order would be 1. And you can go through and solve these and check that that's true, but this pattern is going to repeat over and over again. So to solve something like I the 42nd, your goal is just break this down into things you know. Okay, so I can break this down into, let's say, I squareds. It could be I squared times I squared times I squared. All right, that's getting ridiculous. I'm going to have to write a lot of I squareds. Specifically, think to yourself, how many I squareds am I going to have to write? Give you a pause for thinking effect. And you should all know that you're going to have to write 21 I squareds. Because if you add 21 times, you're going to get 42. So instead of writing out 21 I squareds, I can tell myself, well, I have 21 of these, or I'm going to be multiplying it 21 times. So really, I the 42nd is I squared raised to the 21st. Once again, I squared is just negative 1. And we're raising it to the 21st power. So if I take negative 1 and I multiply it 21 times, or an odd amount of times, it's going to result in negative 1. So if you multiply a negative an odd amount of times, you're still going to have a negative at the end. And so you could simplify it that way. I the 81st is going to be a little bit trickier. You can start to break this down into I squareds. Yada, 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 go on forever. But you're really going to eventually have 40 I squareds. Okay, but if I rewrite this, I squared to the 40th is I to the 80th, right? So that doesn't account for the 81st, which means we're going to need one more I. So this is going to be I squared to the 40th times one more I. This will give me 81 I's. So I want you to finish this off and see if you can simplify it and see what I to the 81st equals. The good news is you have a 1 in 4 shot of getting it right. It's either going to be I, negative 1, negative I, or 1. Try those on your own. Practice forever and ever and ever. Come with questions. Okay, moving on to our next operation. The question is, how do I add imaginary numbers? Now, if you look at these numbers here, these aren't only imaginary numbers. Really, I have a real number here and an imaginary number here. Real number here and imaginary number here. So I'm adding a combination of real and imaginary numbers, and this is actually called a complex number. Please write these down in your notes because I know you're all taking them. And a complex number is just a combination of real and imaginary numbers being added or subtracted together. So we can write this in general as A is our real part and plus or minus our imaginary part. Okay, so this is the real, this is the imaginary. Together they make a complex number. Okay, so our real part is 2, our imaginary part is 5i. Okay, so 5 tells me how many i's I have. The good news is when you're adding complex numbers, it's very similar to just adding numbers in general. So you're going to combine your like terms. How many real parts do I have? How many imaginary parts do I have? Okay, so I have 2 real numbers here, and I add 4 more. That gives me 6 real numbers. I have 5 imaginary numbers, and I take away 3 imaginary numbers. I just have 2 imaginary numbers left. And if you're adding complex numbers, your result should be some sort of complex number as well. So I have a real part and an imaginary part. Even if the real part is 0, it's still a complex number. Okay, you could also add just imaginary numbers. So if I just gave you 5i plus 3i, you would tell me you had 8i, so on and so forth. But keep in mind, you can't add real and imaginary. It's like they're not like terms, like x's and y's. You can't add those. Multiplying them is very similar to multiplying a binomial. Okay, so very similar to how you would multiply, let's say it's 2 plus 3x times 2 minus 3x. You would FOIL it out and see what you get. This is not our problem. We want to try and multiply these complex numbers up here. So same thing, you're going to FOIL. So we're going to start with our first terms, gives me 2 times 2 is 4. My outer terms is 2 minus and minus 3i, so that gives me negative 6i. My inners are positive 3i and a positive 2, so that gives me positive 6i. And my lasts are going to be 3i times negative 3i. So I actually want to write my last terms here off to the side. If I'm multiplying 3i and negative 3i, okay, you're going to multiply your numbers and your imaginary numbers. So 3 times negative 3 gives me negative 9, and I times I gives me I squared. Okay, which is all fine and dandy, but if you think about it, from the earlier in the video, we defined what I squared was. So anytime you see something other than I want you to simplify that imaginary number. So this becomes 4, and these cancel, and we have our minus 9i squared. But I squared we defined to be negative 1. So I can really rewrite this as 4 minus 9 times negative 1. Which, if you simplify that up, you get 4 plus 9, which is 13. So notice, if I multiply the same two terms with the opposite side in the middle, I end up having just a number. That's going to be really important when we're dividing complex numbers. So keep that in mind. But the moral of the story is FOIL stays the same whether you're working with X's, Y's, happy faces, suns and moons, or imaginary numbers. Okay, the only difference is when you multiply I times I, that's really defined as negative 1. So you're going to want to substitute that in anytime you can. Next one, divide 3 plus 5i over 4 minus 2i. Remember the rule where you can't have any radicals in the denominator that we talked about earlier? Well, that rule is going to come into play with imaginary numbers as well, okay? Every time you divide by imaginary number, you're going to have to find a way to get rid of it. And that's why I talked about this problem, because when you multiplied by the same two terms in the opposite side in the middle, all of the imaginary numbers canceled out, went away, and we were left with just 13. And if you remember from our unit on radicals, this is called multiplying by the conjugate. For example, the conjugate of 4 minus the square root of 2x would be 4 plus the square root of 2x. Okay, those were conjugates. And you multiply them, you got rid of the radical way back in the day. The difference here is we're working with conjugates of complex numbers. So this is now going to be called the complex conjugate. Complex conjugate. And the complex conjugate will get rid of any imaginary numbers in your denominator, similarly to how we got rid of the imaginary numbers in this problem. So the complex conjugate of 4 minus 2i is going to be 4 plus 2i. And whatever you multiply by the denominator, you also have to multiply by the numerator. Okay, so you can go ahead and FOIL all of these terms out in the numerator and denominator, so on and so forth. I want you to finish this problem up on your own, okay, because it's really practicing multiplication as well. Simplify it, get rid of your i's, substitute in any I squared as negative 1. And if you have questions, sorry for the bell. If you have any questions, you can come back and ask me the next day. So, have a good night of studying. Study imaginary numbers, practice on your homework, and good luck.